Okay, so this is going to be glycogen breakdown and glycogen synthesis. So what is that? What is glycogen? It's a polysaccharide, right? It's made of alpha-1,4, alpha-1,6 branches. What does this mean? So say we have glucose, right? Glucose is a single monosaccharide. It's just a one sugar molecule. You join these together, multiple of them, right? This is called a polysaccharide. Multiple monosaccharides put together. All of these combined is going to form, say this is one branch, and then we have another branch that branches off of it going this way. This will be an alpha-1,6 branch, this will be an alpha-1,4 branch. All of these branches combined are going to form glycogen. Okay, so now we have to figure out how we make that and how we break that down. So, glycogen in skeletal muscles, right? Or glycogen in the liver. It's two different ways to do it. Synthesis of glycogen is called glycogenesis. Glycogenesis. What does genesis mean? New, like to create something new. And glyco is glycogen. So new glycogen, right? Glycogenolysis, glycogen again. But what does lysis mean? Lysis is to break down. So you're breaking down glycogen. Okay, so now you have that. Why do we want to break down glycogen, or why would we want to use glycogen? Okay, so for breaking it down, right? The first thing we need to know before we even talk about glycogen is how our bodies work. Say we're about to run a 1 mile race, right? You're doing a 1,600 meter run. The first 4 to 6 seconds of this run, you're going to use ATP. This is just free energy in the body, right? You just have it in the body, and it's going to last for 4 to 6 seconds. After that, you're going to use something called creatine phosphate. Creatine phosphate, we're going to talk about how this is created and broken down in a little bit. But this is going to be used for the first 15 to 20 seconds. After the 15 to 20 seconds, right, say you're about 200 meters into the race, depends how fast you are, maybe 150 meters, you're going to start breaking down glycogen. So if you break down glycogen, you're going to break it down into two ways. Step one is going to last about 40 to 60 seconds, right? And this is going to be anaerobic glycolysis. After you break down glycogen for 40 to 60 seconds, right, your body's going to start slowing down. You can't run for a minute straight as fast as you can. Your body's just not able to do that. You're going to start going into aerobic glycolysis. Okay, and the type of glycolysis that you're going to start using depends on the amount of oxygen supply that you have. And how do you determine that? It depends on the fiber type, so the muscle type. We know type 1 muscle fibers, right, they're slow twitch, so you could run for hours using these muscle fibers because they're using aerobic, right? Now anaerobic is going to be type 2 muscle fibers. They're white muscle fibers, and they have what? They're very fast contracting. They don't have a lot of mitochondria in them. They're strong. Okay, and then after that, you could use, after like about 90 minutes to 120 minutes, you start using fatty acids, right? And this is only aerobic glycolysis. But I want to just mainly talk about glycogen. So in this chart right here, I'm going to show you glycogen, like how you build it up, and then it's going to progress, and it's going to show how you break it down. It's all going to be one flow chart. So to start, glycogenesis, right? It occurs where? In the cytosol of the liver and of the muscles. So this is where this process occurs. Liver and muscles. Okay. So you're eating food, right? You start to ingest food into your body, right? It's a carbohydrate because it's glycogen. So you invest a carb, a CHO, right? Carbohydrate. This carbohydrate is then broken down into glucose. Okay. This glucose is then what? Remember in glycolysis, we have an enzyme called glucokinase. This is going to be for the liver, or hexokinase for the muscle. These enzymes are going to turn glucose into glucose 6-phosphate. Okay, so now, there's two different paths. One path, we could go from glucose 6-phosphate down through glycolysis, right? If you go through glycolysis, you're going to form pyruvate, which is eventually going to help you produce ATP, right? But we're not breaking down glucose. We're not doing glycolysis. The goal here is glycogenesis. We're trying to make new glucose. Glycogen, genesis, new, right? Make new glucose. Okay, so instead of going through glycolysis, we're going to go through phosphoglucomutase. It's another enzyme. This phosphoglucomutase is going to convert glucose 6-phosphate into glucose 1-phosphate. After that, we're going to have another enzyme called UDPG pyrophosphate. What is this going to do? So he's going to use UTP, right? Uridine triphosphate, and he's going to give this group, this glucose 1-phosphate, it's going to give it 2 phosphate groups. So it's going to give it a diphosphate. When that happens, this glucose 1-phosphate is turned into UDP glucose. What is UDP glucose? So UDP glucose is not really used for the creation of new glycogen. It's kind of like a bus, right? Think of a transporter, like a car or something. I think of it as a bus because public transportation, and it can move things either way, but it just moves the glucose to its proper location. So like here's an example. If you have glucose monomers, right? This UDP glucose takes the glucose residues and stuff and it puts it in the proper spot to make proper branches. That's the only reason why I think of it as like a bus or like a train. Okay, so now UDP glucose, right? Before it gets converted into glycogen, it goes through another process. It branches off, right, into this region, and then it's combined with another thing. So we have a protein here called the glycogenin, right? Glycogenin comes and fuses together with UDP glucose, right? They fuse together and they form something called a glycogen primer. This glycogen primer is going to be used for another, it's going to have another role. What is his role? So after UDP glucose does this, right? It forms the glycogen primer. It gets converted down via glycogen synthase into glycogen. So this glycogen primer is a coenzyme, so it's in the reaction, right? It's get pushed into this reaction via glycogen synthase, and it becomes UDP. This UDP glucose becomes glycogen. But what type of glycogen? All it becomes is the linear chain one. So the one we talked about was just the alpha 1,4 branches. It doesn't have a branch on it yet. It's just alpha 1,4, a linear chain. So it's an alpha 1,4 chain. Now, before I keep going down, the process that I just talked about right here, this glycogen primer, right? It's called autoglycosylation. What does that mean? Autoglycosylation is just UDPs, right? Adding more groups onto them. And it can only do this for up to like 4 glucose molecules before it's got to be used for this branching enzyme. For the glycogen synthase. So these 4 glucose molecules can be then, via using an enzyme, converted into glycogen. But just adding on to each other, it's just UDP. Okay. Now, glycogen, alpha 1,4, the glucosal units, right, is then converted into glycogen, alpha 1,4, alpha 1,6 glucosal units, right? How does it do this? It uses a branching enzyme. What is this branching enzyme going to do? So he's going to cut, this is a long chain, right? This is a long chain polymer of glucose, right? He's going to cut off at around 6 to 8, right? About 6 to 8 molecules. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I have it at 7. 6 to 8. It's going to cut this chain off, and then he's going to add it to this linear chain, this 1, 2, 3, 4, right, etc., the alpha 1,4 chain. So here, you have the alpha 1,4 chain, just a straight linear chain. This branching enzyme makes a cut to a random, another polymer, and then it adds it to the linear chain. So now you have a branched chain of glycogen. Alpha 1,4, alpha 1,6, alpha 1,4, alpha 1,6 branch. Okay. This is how glycogen is now stored in the liver and in the muscles of our body. So now, how do we take this glycogen molecule, right, and now convert it into glucose? So, when are we going to use this stage? This stage is only going to be used when we're resting, right, or we just consume a big meal and we're trying to restore muscle glycogen, restore our sugar levels. Okay, but now, say we're fasting, right? We're working out for 1-2 hours, or we woke up and we worked out without eating. We need to break down this glycogen. Mainly the glycogen that you're going to break down originally when you come from fasting is from the liver. But after you break down the liver glycogen, you're going to use muscle glycogen. Why? How do you determine the difference? So liver glycogen contains 100 grams, right? You could store about 100 grams of carbohydrates in the liver, which equates to about 400 calories, right? So you're working out hard for a good 1-2 hours, and you finally deplete most of the carbohydrates in the liver. After you do that and you're still working out at a high intensity, you're going to have to start breaking down the carbs where? In the muscles. The muscles hold about 400 grams, right? And then in the blood you always have carbs in it. The blood stores about 5 grams, but this is not really something to dwell on. Actually, the liver, it's more like 95. So your total body could store a total of 500 grams of carbs. But that's just a side thing. So now, say I'm taking this glycogen, right? The alpha-1,4, alpha-1,6 glycogen, and I'm going to break them down into glucose. I want glucose back into our body because what? I want energy. Glucose makes energy by glycolysis, converting it to ATP. So now, here we go. If I use an alpha-1,6 glucosidase debranching enzyme, I'm going to turn this glycogen into glucose in the muscle. Okay, so in the muscle, the glycogen gets converted into glucose via alpha-1,6 glucosidase. It's a debranching enzyme. What does debranching mean? All it means is taking this branch and knocking it off. Knocking off a little polymer. A monomer, I'm sorry. Okay, so now, keep proceeding up, right? We can do two different things. Glucose 1-phosphate is now created via glycogen phosphorylase. If you guys notice, most of the words I wrote in purple are the enzymes. I don't know why, I just like writing all the enzymes in purple. So if you see a word in purple, 95% of the time it's an enzyme. Except over here, glycolysis, that's not an enzyme. Okay, so now glycogen phosphorylase, right, is going to make glucose 1-phosphate. It's going to be the same glucose 1-phosphate over here, but we need where is it coming from? This time it's coming from glycogen. So this glucose 1-phosphate, right, this step creates glucose 6-phosphate. So right here we had glucose 6-phosphate going to glucose 1-phosphate via phosphoglucomutase. This is a reversible reaction, meaning it could go either way. So now glucose 1-phosphate could become glucose 6-phosphate via the same enzyme, phosphoglucomutase. So phosphoglucomutase makes glucose 6-phosphate. Now, we could go two different directions. We could go through the muscles or we could go through the liver. So if we're going through the liver, right, because we're going to need to have glucose in our liver for it to function as well, we're going to use an enzyme called glucose 6-phosphatase. Glucose 6-phosphatase then converts glucose 6-phosphate into glucose. This glucose is then what? Broken down and it's released into our blood, and this glucose in our blood is going to go right to our brain. Our brain needs the glucose to function. That's why the glycogen that's broken down into glucose into the liver is mainly used for the brain. Now, if we want to go through the muscle, right? I have glycolysis right here. I don't know why I wrote it in purple, but I did. This glycolysis, glucose 6-phosphate, could then go through glycolysis and become pyruvate. It does not use glucose 6-phosphatase. We know that this enzyme is not used in glycolysis. So this glycolysis becomes, this glucose 6-phosphate can become pyruvate, and then it can be broken down into two things. It can get broken down into lactate or acetyl-CoA. Lactate is for what? Anaerobic glycolysis, right? And a byproduct is lactate. And acetyl-CoA is for what? Aerobic glycolysis. And it enters what? The TCA cycle. Okay, so that's basically the flow chart of how glycogen is created and then how it's broken down. Hold on. Is it bright? Okay, so now we spoke about the breakdown of glycogen, right? And we spoke, the formation of glycogen into the muscle and the liver. And we also spoke about the breakdown of glycogen from the muscle and liver into glucose. Now I kind of want to talk about how it's regulated. So why does glucogenesis start and why does glycogenolysis start? So we need to know that there's 3 ways to regulate these steps. One way is called hormonal, another is allosteric, and the third is calcium. It's not really called calcium, but it's a way to regulate it. So hormonal is by phosphorylating or dephosphorylating something. So what does this mean? If you turn something on, something else turns off. So if you turn on glucogenesis, glycogenolysis is going to turn on. If glycogenolysis is on, Glucogenesis is going to be off. They inhibit each other. Okay. So now, regulatory enzymes. The two enzymes we need to know. Glycogen synthase, glycogen phosphorylase, right? These enzymes are also reciprocally inhibited. Glycogen synthase is for gluconeogenesis, right? You're synthesizing glucose, synthase. So I'm just going to write here, gluconeogenesis. And then glycogen phosphorylase, you're phosphorylating glycogen. So you're breaking it down. So that is what? Glycogenolysis, right? Okay. So now the first step. I have it broken down into two different charts, if you could kind of tell. These are two different charts. So the first one, I'm going to talk about how you turn on and off glycogen synthase, right? Okay. So now, in ATP production or AMP production, right? You go ATP to cyclic AMP, also known as adenyl cyclase, into AMP. Okay, and how are these regulated? So epinephrine, right? This is in muscles. Remember, epinephrine isn't for muscles. Epinephrine is what? Fight or flight stimulus. It's a hormone. Okay, so epinephrine is going to activate adenyl cyclase, right? This adenyl cyclase is then going to turn ATP, right? Well, it's not even turning it into, but this adenyl cyclase is activating CAMP. What is CAMP? Cyclic AMP. Why would you want cyclic AMP? Okay, cyclic AMP creates PKA, protein kinase A. And what does protein kinase A do? So if we have PKA over here, right? Protein kinase A, and we have a lot of stored glycogen, right? But we're running out of energy. Our energy stores are low. We want to take one of these molecules, right, and make it a free glucose so we could use it to make ATP, right? So what's going to stimulate this? Epinephrine. A fight or flight response, you're going to need a lot of energy, so you want to break down this glycogen. Okay, so how are we going to do that? So now, this PKA, right, is then going to be stimulated with an ATP and an ADP. Now, if we're doing this, what are we doing? We're not breaking down glycogen. We're turning glycogen off. So we're inactivating glycogen synthase. How? So if we have a lot of energy, so I drew this whole step, right? But now if we have a lot of ATP, a lot of energy, right? This ATP could come, phosphorylate PKA, right? So give it another phosphate, makes it become ADP. We phosphorylate glycogen synthase. If glycogen synthase is phosphorylated, it means it's off. Now, how do we turn glycogen synthase on? So what are we trying to do? We're trying to make more glycogen, all right? If you're trying to make more glycogen, you don't want to be turning this off. You want to be turning him on. How are you going to turn him on? So you're going to turn him on using insulin. Insulin is going to activate something called phosphodiesterase, right? Phosphodiesterase right here. He's going to activate phosphodiesterase. Phosphodiesterase is going to remove the phosphate. So this P that I put on glycogen synthase gets removed. This phosphate gets broken off, right? Off of this glycogen synthase. And now we have a glycogen synthase without a phosphate. So this phosphate's not here. When that phosphate's not there, that means it's active. We're in the active form. If we're in the active form, we're making more what? Alpha 1,4, alpha 1,6 branched glycogen molecules. Good. Now, if we want to break down glycogen, right? And we want to form glucose molecules, like I said before, if you want to break one of these off and form these guys, you're not going to use glycogen synthase, you're going to use glycogen phosphorylase. Why? Because phosphorylase breaks down the glycogen molecule. Okay, so how are you going to do that? So, unfortunately, it's not as easy as this process because it's reciprocally inhibited. So in order to turn on glycogen phosphorylase, what do you need to turn off first? You have to make sure glycogen synthase is off. Okay, so now, two ways. You can do it through glucagon or an epinephrine, right? This is for the liver. This is only for the liver, so you're breaking it down. So now, we know CAMP, right? Cyclic AMP gets converted into PKA. ATP, phosphorylase, right, ADP, and we form phosphorylase kinase, right, with a phosphate on it. If we have phosphorylase kinase with a phosphate on it, that means it's in its active form. If it's in its active form, what happens? Okay, so we have another step, step 2. If phosphorylase kinase is activated, another ATP comes and makes ADP. What is this going to do? This ADP adds a phosphate to what? Glycogen phosphorylase, and now we have glycogen phosphorylase with a phosphate on it. If we have glycogen phosphorylase with a phosphate on it, we're in the active form. What does this mean? Glycogen phosphorylase in the active form is doing what? We're taking off one of these monomers, right, and we're using it as energy. We're phosphorylating glycogen. Now, how do we stop this? What if we want to stop breaking down glycogen? We want to make glycogen now. Okay, well, we have to turn him off. So how do we turn him off? Insulin, right? So it's going to be off when you have a lot of sugar in your bloodstream. So that means insulin is being secreted. Insulin is going to then what? He's going to remove a phosphate off of this glycogen phosphate with the phosphate on it, and it's going to form glycogen phosphorylase without a phosphate. So this P is gone. If this P is gone, glycogen phosphorylase is inactive. It's only active in the phosphorylated form. Okay, so now if that happens, what's going to occur? That means this phosphorylase kinase, right, is going to get dephosphorylated. So he's dephosphorylated, and he's going to form phosphorylase kinase without the P, meaning he's inactive. So if he's inactive, what? This whole process can occur. So now if he's inactive, what can occur? Glycogen synthase. Glycogen synthase is then going to start making more glycogen. Okay. That's a lot, but I don't know, it's the best way I could explain it. Just the key parts, parts to remember is that glycogen synthase is active when it's not phosphorylated. Glycogen synthase is inactive when it's phosphorylated. So dephosphorylated on, phosphorylated off. Glycogen phosphorylase, right? When it's phosphorylated, it's active. When it's dephosphorylated, it's inactive. So dephosphorylated inactive, phosphorylated active. That's for glycogen phosphorylase. Phosphorylase kinase, right? Phosphorylated means it's active. Dephosphorylated means it's inactive. So dephosphorylated, phosphorylase kinase, inactive. Phosphorylated, phosphorylase kinase, active. Okay, so now to finish the hormonal regulation, I just want to talk about how the liver and muscle are kind of affected a little differently. So glycogen, this is for the muscle side. So glycogen gets converted into glucose 1-phosphate, right? Via glycogen phosphorylase, breaking down of glycogen. What inhibits him? Okay, so if we have high levels of ATP, or if we have high levels of glucose 6-phosphate, we're not going to want to break down to glucose 1-phosphate, right? There's no need for it. We don't need to break down glycogen because we already have the main, I don't know what this even is. The main product for glycolysis, right? Glucose 6-phosphate then gets converted into glucose G6P, fructose 1,6 bisphosphate down into pyruvate. So we already have a high level of him. And if we have a high level of ATP, that means we have a lot of energy. We're not going to need to break down glycogen into glucose 1-phosphate. There's no need for it. Now, if we have a lot of AMP, so adenosine monophosphate, that means ATP is what? Low. If ATP is low, AMP is high. If AMP is high, we want to break down glycogen to glucose 1-phosphate. So we're going to stimulate glycogen phosphorylase. Now, how are we going to make more glycogen? If we have a lot of glucose 6-phosphate, right? So he's not going to want to break down because we have a lot of him. What are we going to do? We're going to try to build him up. We're going to activate glycogen synthase via glucose 6-phosphate. Now for the liver, it's kind of similar, a little different. Glycogen to glucose 1-phosphate, right? Glycogen phosphorylase. What's going to inactivate him? high levels of glucose 6-phosphate, just like the muscle, high levels of ATP, just like the muscle, but also high levels of glucose. So if you have high levels of glucose in the liver, you don't want to break down more glycogen and put more glucose into the liver. It's an easy way to get diabetes, right? More and more glucose is going to raise your blood glucose levels because the liver glucose goes to your blood and then to your brain. And then this is going to be pretty detrimental. Now, if you have glucose 1-phosphate, right, and you want to make more glycogen, what are you going to use? Glucose 6-phosphate, he's just going to upregulate glycogen synthase. That's really the main regulators for glycogenolysis and glycogenesis. So now some allosteric regulators, glucagon, epinephrine, and insulin. What does that mean? So that means if glucagon, these usually come in pairs. I mean, only for the liver. If it's muscle, it's only epinephrine. But if we're talking about the liver, if glucagon or epinephrine is on, that means insulin is off. If insulin is on, that means glucagon and epinephrine are off. That's all the allosteric is. And now calcium. This is the last one. If you have high levels of calcium, right? Calcium is going to stimulate calmodulin, which is a protein. This calmodulin is then going to stimulate pKa. Why is this helpful? Well, if you're already stimulating pKa, you don't need to use CAMP, right? You don't need to turn on CAMP via glucagon or epinephrine. This pKa is used from CAMP, from adenylyl cyclase. So all calcium is going to do is help upregulate the pKa process. Okay, now, question that I want to talk about. Down here. A 42-year-old man administered a compound that eventually causes an inhibition of the enzyme phosphodiesterase. So, an inhibition of this enzyme. What other enzymes are most likely going to be decreased with it? So, if we go through the list, right, we see adenylyl cyclase, glycogen synthase, phosphoglucomutase, phosphorylase kinase, or protein kinase A. So now, let's first look. An inhibition of what? An inhibition of phosphodiesterase. Okay, so if we have an inhibition of this guy, right? We know he's here. And where else? He's down here. Okay, so now, if phosphodiesterase is inhibited, what is he not making? Phosphodiesterase comes from where? Phosphodiesterase comes from insulin, right? So if we have insulin right over here, insulin is stimulating what? Phosphodiesterase. So let me write it here for you. Phosphodiesterase. And what is this phosphodiesterase doing? This phosphodiesterase is removing the what? The phosphate. So if you're not able to remove this phosphate, you can't activate glycogen synthase. Why? Because phosphodiesterase is not taking the phosphate off of glycogen synthase. Meaning, he's staying in this position. He's staying in the inactive state. So this enzyme is going to be decreased. Now, if it said adenyl cyclase instead of phosphodiesterase, what's going to happen here? So where is adenyl cyclase used? Right over here. So now, if we have a decrease, right, in adenyl cyclase, what's going to happen? You're also going to decrease what enzyme? So if adenyl cyclase isn't on, CAMP can't be stimulated, can't stimulate pKa. If this can't be stimulated, you can't phosphorylate glycogen synthase. What is going to be phosphorylated? Glycogen synthase is going to be active, so what's going to be inactive? Glycogen phosphorylase. Remember, they reciprocally inhibit each other? So if he's on, glycogen phosphorylase is off. So if you have a decrease in adenyl cyclase, that means you have an increase in what? Glycogen synthase. Now, if they talked about, we could do phosphoglucomutase, where is he? Phosphoglucomutase is used for which step? He's used over here, right? He's going glucose 1-phosphate to glucose 6-phosphate. Are there any enzymes that are really controlled by this process? Maybe glucose 6-phosphatase? He might be the only enzyme that's decreased, but other than that, there's no other stimulating factors. So you could eliminate him. Phosphoglucomutase, you could eliminate adenyl cyclase. Now, what about phosphorylase kinase? Or what about protein kinase A? They're kind of like the same thing, right? But let's do phosphorylase kinase first. If phosphorylase kinase is inhibited, what's going to occur? Okay, so if he's not active, what happens? We can't stimulate glycogen phosphorylase. Okay, so if glycogen phosphorylase isn't on, we can't have an active form and we can't break down more glycogen. But that has nothing to do with phosphodiesterase. So you can eliminate him. And now what about protein kinase A? So if you inhibit protein kinase A, okay, if he's inhibited, you know insulin is activated because these are reciprocally inhibited as well, right? Glucagon and insulin. If glucagon's on, insulin's off. But if insulin's on, glucagon's off. Okay, so if PKA is inhibited, that means glucagon is off, insulin is on. If insulin's on, phosphodiesterase is on. Phosphodiesterase is on, you make glycogen synthase. So you're not inhibiting phosphodiesterase, you're stimulating him with turning off PKA. So this is wrong too. So the only one that could be is glycogen synthase. So these are the glycogen storage diseases, right? They can affect both glycogenolysis and glycogenesis. Apparently, the most important one that they want us to mention is type 1A. This is known as von Gerke's disease. And what is von Gerke's disease? It's a deficiency of glucose 6-phosphatase. What was glucose 6-phosphatase used for? Only in the liver, right? So if he was only in the liver, what's going to happen? So if you have glucose 6-phosphatase, you can't break down what? You can't break down glycogen into glucose because this is one of the steps. Okay, so if that happens, what's going to occur? You're going to get hepatomegaly, which is an enlarged liver. Also, this occurs in the kidney, and if this glucose 6-phosphatase is inactive in the kidney, we didn't really talk about the kidney breakdown, but I'll mention it quick. You're going to get renomegaly, right? Enlarged kidney. Okay, so what are the clinical signs for a person who has this disorder? They're going to have a doll-like face look and a protruding abdomen. I don't know why they'll have a doll-like face look, but a potential reason why they'll have a protruding abdomen is because their kidneys and their livers are enlarged. So their abdomen is going to be enlarged because your internal organs are right by your stomach, right? Okay, so if you have a deficiency in this, what's going to occur? Okay, so we know you can't break down glycogen, right? If you can't break down glycogen, you can't have glucose. If you can't have glucose, what's going to happen? You're going to go to fasting hypoglycemia. What is hypoglycemia? Low blood sugar, aka low blood glucose, right? Okay, so if you have a low blood glucose, what's going to occur? A couple different things. You could have severe lactic acidemia. You could go through ketosis. You could go into hyperlipidemia. You could have a fatty liver, or you could have hyperuricemia. So, one of them I want to talk about, not the main one, but like a really important one, is hyperuricemia. What is this? Okay, so we know in purine pyrimidine synthesis, right? We take purines, we take pyrimidines, right? Mainly purines though. And what are we going to form? The whole process, right? You form eventually urea. And urea gets excreted through the kidneys, right? Now, if you have had fasting hypoglycemia, some functions are going to be upregulated. What are these functions? Okay, so in the pentose phosphate pathway, we have to remember in purine pyrimidine synthesis, right? In order to make purines, you need what? You need ribose 5-phosphate, right? This is the sugar that gets attached to the purine. And what is a purine? Adenine or guanine. So this sugar combines with the purine with I think it's PYPP, pyrophosphate, PRPP, PYRP maybe. Okay, so this ribose 5-phosphate comes from the pentose phosphate pathway. Okay, and this helps what? It helps form purines. And what were the purines? GDP or ADP. Okay, so now, if this phosphate, right, is upregulated, you're going to make more purine nucleotides. And if you're making more purine nucleotides, what's going to happen? You're going to form more uric acid. Okay, so if you're in a fasting state, the pentose 5-phosphate pathway is upregulated. So ribose 5 is upregulated. So this PRPP goes into purine and pyrimidine synthesis, and you form urea. If you have more urea, that means, or if you form more purines and pyrimidines, you're going to form more urea, more uric acid. And what does uric acid lead to? High levels of uric acid. High levels of uric acid leads to gout. So this is how you're going to have gout. So if a patient comes in and they give you all these disorders, blah, 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 and you can't figure out why they have gout, it's a good idea to check if they're hypoglycemic or not. Because if they're hypoglycemic, that means they have a low blood glucose level, thus stimulating pentose 5-phosphate, ribose 5-phosphate, purine synthesis, purine catabolism, the breakdown, uric acid, gout. Okay. Also, what else can occur? Talked about lactic acidemia. What is lactic acidemia? Okay, so this is a deficiency also with the glucose 6-phosphate, and it's going to add lactic acid to where? The kidney. Okay, so we know, I don't know how to draw a kidney too well, so I'm just going to write a little square, I'm going to write a kidney, right? Okay, so uric acid, right? Uric acid gets processed where? Through the kidney. Okay, now if we have lactic acidemia, so we have a lot of lactate, lactate also gets processed through the kidney. Okay, so now I'm going to give like a little example. This is really not accurate, but this is the best way that I remember it by. Say the kidney is able to excrete 100 units, right, of a toxin or of substances, right? Thus, uric acid or lactate, for an example. And the body says, at a normal stage, you could decrease 50 units of uric acid, and you could eliminate 50 units of lactate. Okay, now, we're in a hypoglycemic state. Uric acid production is increased. Let's just say this uric acid production is at a normal stage, right? It stays at 50. Lactate production is definitely increased, right? So if you're increasing the amount of lactate, what's going to happen? Instead of being at 50, you're going to become 75. So now, if you normally release 100, but your kidney is fighting to release 125, there's a negative 25 loss, right? You can release 25 of these units. If you can't release 25 of those units, what's going to happen? Okay, well, you're going to have some potential liver failure, kidney failure. What happens if you have kidney failure? Well, you could have uric acid buildup, and that's another way you could lead to having gout. Okay, so that's just a little dumbed down example, but it helps me remember it. Now, what is hyperlipidemia? Okay, so if you can't break down blood glucose, right? You can do glycolysis. What are you going to do? You want to use a TCA cycle. You want to break down fats. So you're going to increase the amounts of acetyl-CoA, which is going to increase the amounts of fatty acids. Why does this increase fatty acids? I don't know. My teacher said no one knows why, and it causes hyperlipidemia. So that's basically that. The next type of deficiency is type 1B, glucose 6 translocase deficiency, right? So it's a type of type 1A, but instead of glucose 6 phosphatase, it's glucose 6 translocase. And what does this affect? This is going to affect the transfer of glucose from the cytosol into the rough endoplasmic reticulum, and it's going to cause neutropenia and recurrent infections. Okay, so now, that's type 1. This is the main one. Other ones we're going to talk about is going to be Pompei's or Pompey's, Corey disease, Anderson's disease, McArdle syndrome, and Her's disease. Okay? So, Pompei's disease, type 2, right? Type 2 for Pompei's disease is the second one. And this is a lysosomal disorder. What does that mean? So, glycogen is also degraded in the lysosome. It's not just degraded in the cytosol. It's also degraded in the lysosome. Not a lot, but just a little bit. Okay, so now, if this alpha-1,4 glucosidase, right, the enzyme that is responsible for breaking it down, is not working, this lysosomal disorder is inactive, and what's going to occur? You're going to have massive cardiomyopathy, so an enlarged heart, And it usually happens when you're a baby, and the child usually has a heart attack and dies by the age of 2. Now, if this occurs when you're an adult, you get muscle dystrophy. Now, what's type 3? Type 3 is Cory's disease. Okay, so I don't know if this is dumb or not, but this is how I remember it. 3, C, third letter in the alphabet. After C becomes D, so Cory, now D, debranching, CD, debranching enzyme. What does the debranching enzyme do? So you're going to have an abnormal type of glycogen, right? Glycogen is not going to be how it's supposed to look. You're going to have glycogen with shorter branches because you're not going to be able to debranch it well. And what are you going to have? You're going to have a lot of these branches. So you're going to have a lot more of the branches, and they're also going to be shorter. This is going to cause hypoglycemia, which is going to cause hepatomegaly in infants. Now, type 4, Anderson's disease. A, what comes after A in the alphabet? B. So this is a branching enzyme deficiency. Similar to debranching, but now it's branching. The branches are going to be too long, and there's not going to be a lot of them because you're not going to be able to make new branches. So there's going to be few branches. This is going to lead to heart failure. Next one, type 5, McArdle's syndrome. I don't know, M for muscle maybe. McArdle syndrome, muscle glycogen phosphorylase disorder, right? You're going to have a low blood lactate, so you're going to have a poor exercise tolerance. So if someone's running, right, and they cramp up really fast, it's because they're not producing lactate. Lactate is a buffer. If you can't create lactate, you're going to have an increased level of myoglobinemia or myoglobinuria. This is also going to be shown as myophosphorylase in like blood tests. The last one is type 6, BI, Her's disease, right? This is a glycogen phosphorylase in the liver disorder. It's not really a bad diagnosis. It's actually a good diagnosis if you have a glycogen storage disease, if you have this one. And it just leads to mild hypoglycemia. So you have to be able to regulate your blood sugar a little bit better. So those are the glycogen diseases. Okay, so the last thing I want to mention is creatine. Remember I said creatine lasts for about 15 to 20 seconds, but how is it really used? So before I talk about it, I just want to mention creatinine. This is what's excreted in your urine. So it's an end product of creatine. So there's 3 different types. There's CK1, CK2, and CK3. But before I talk about the types, let's talk about what creatine actually is. It's made from arginine, glycine, 2 amino acids, and S-adenosyl methionine, which is known as SAM. What is SAM? It just donates a methyl group, does it in nucleotide synthesis, etc. Okay, so the creatine reaction is creatine to creatine phosphate, right? All it really is. So now, if you're at rest, right, your muscles want to make more creatine, right? You don't want to make more creatine, you want to make more phosphocreatine. Why would this be important? So if you're making more phosphocreatine, you're making more creatine with a phosphate on it. Phosphates are used for what? Multiple different things, but in this instance, it's going to be used for energy. So how are we going to make this PCR, phosphocreatine? We're going to go creatine plus ATP, and it's going to turn into creatine with a phosphate on it, and ADP. Okay, so this phosphate breaks off, and it becomes ADP, but the phosphate's added to creatine phosphate, right? It's going to be a storage form. So I have up here, just like an abbreviated version, I remember it better. CR plus ATP goes to PCR plus ADP. Same exact thing. Now, if your muscles are contracting, right, you're working out, and you're doing the 15 to 20 seconds, right? You go through that ATP in 4 to 6 seconds, right? That was the first step. Second step, creatine phosphate, 15 to 20 seconds. What's going to happen? So you're going to have that ATP is getting depleted, right? When ATP gets depleted, what does it turn into? ATP gets turned into ADP. Now, for quick reactions, right, you don't want to go through glycolysis. You don't want to go through the TCA cycle, right? You want to make more ATP with this guy. How are you going to do that? Okay, so that storage form that you just built up, the creatine phosphate, you're going to take PCR, you're going to take the phosphate on him, you're going to give it to ADP, and you're going to form ATP. So let's see it. So now, creatine phosphate, creatine P, as known as PCR, same thing, right? Plus ADP. So that ATP that was used in that 4 to 6 seconds, that phosphate was used, now it's ADP, gets converted into creatine, so CR, same thing, plus ATP. So the phosphate over here, right, comes off, this P comes off, and it gets put onto this guy, and it forms ATP. What can this ATP be used for? Energy. And this happens for about 15 to 20 seconds before you got to start going through glycolysis, anaerobic and aerobic, and then starting fatty acid synthesis with beta oxidation, etc. Okay, so that's basically all you need to know about the functions of creatine for like skeletal muscle use. But now there's three main things that it's also used for. And we have CK1, CK2, and CK3, right? Three different types. Creatine kinase 1, creatine kinase 2, creatine kinase 3. CK1 is used for the brain. The ones I'm going to talk about are the heart and the muscle, though. So the heart. If you go in for a scan, right, or a lab, you go to see the physician, he's going to test for high CK2 levels, right? Also known as CKMB. What is CKMB? It's creatine kinase myocardial bands, right? That's the long name for it, but everyone calls it creatine kinase MB, a CKMB. And if you have high levels of CKMB, right, you have a lot of creatine floating around in the heart, you're going to cause myocardial infarctions, right? Infarctions. This is going to be problems to the heart. Very dangerous. Now, in the muscle, your muscles are constantly breaking down, right? You're constantly excreting creatine. What's going to happen? Creatine gets converted into, we said, creatinine in the urine, right? And now the doctor or the doctor's going to order a lab test, and he's going to test in your urine and your plasma the levels of creatine. Creatinine, not creatine. Creatine is the product that's used in muscle contraction, but when it's broken down, it's creatinine, and it's excreted. So the nephrologist orders that test. If he sees high levels of creatinine, that means you have kidney problems. If you have kidney problems, you could have renal failure. So it's just a biomarker, basically. So high levels of CK2, heart problems, high levels of CK3, muscle problems, kidney problems. High levels of CK1, I don't know, but I know it's for the brain. And just remember that it's made from arginine, glycine, and SAM, S-adenosine methionine. That's it. Hope it helped.